say this body's ideal transfer function, it has proven useful to design that the, you can say, fractional filter PID control using the principle of IMC, internal model control. So that is Bode's ideal transfer function. So you can say that what is the meaning of Bode's ideal transfer function? Bode has worked on its sensitivity integrals. That is also missing in the literature. It is not well taught. Only Bode plot it is taught, but you can say you can focus on what are the Bode's original, means that work compilation. So you can find Bode's ideal transfer function, Bode's sensitivity integral, and Bode plot. So these are important work, and people they have, and these can be understood also. So it is there. There is another question: positive feedback, negative feedback, mixed feedback. Everyone understands that the positive feedback, negative feedback, but there is another term, mixed feedback also. So now feedback is not only positive and negative, but there is a combination of positive and negative also. So you can think of mixed feedback. Just I am coining few words. And this slide, this presentation I made several times, but okay, that this would be useful each time that some new content would be there. So yeah, this is the mixed. I recommend you to those who are new people in control that they wish to pursue. So mixed feedback, what it is, biological systems, it has applications. This is Henrik Wade Bode, what that European name that you can say, if I'm correctly saying, but his name is ESW Bode, Network Analysis and Feedback Amplifiers. This is very old book. There is a very famous book on network analysis, Van Valkenburg. If you see turn the pages of that book, and bibliographic detail are there, so you will find this book. And certain papers sometimes, that if you say nonlinear dynamics or control literature journal papers, so they cite this book. And this book, it was published in 1945, and this has 545 or more than 500 pages, around 550 pages, and you can find at the web also. I have this book, because why this book is there? There are many great books are available in the literature nowadays, but the point is that he was pioneer. If you read his book, then you can understand what ideas he had in his mind that led to all these plotting. So older books are also important sometimes. Why older books are important? Because older books are written by discoverers, and those books tell what discoverer has in their mind. So I recommend you to see this book. It is scarcely studied, but found, but in journal papers, and then you can say that the references you can find. And this is the book in World War II, that this World War II or World War II post World War. This book during World War, that this book was widely circulated and huge demand was there. So that across the globe, those who were looking from that the control viewpoint, because technology was used, so this book was huge in demand. So you can see this one, ESW Bode, mixed feedback, and these books which are scarce that I am discussing. So Gunter Stein, that you can say, respect the unstable IEEE control systems magazine, because magazine and transactions, there are difference. Transactions are focusing, those who are doing research, they publish new results, but that they work on the problems, they publish on a specific problem. And analytics is too much, experiments are too much, originality is too much. But magazine, that is certainly originality is there, but pedagogy would be there, historic account would be there, and simple equations would be there, and applications would be there. So magazines, papers, and transaction papers. Transactions, if you talk about, then huge analytics would be there, applications would be there, experimentation would be there, there would be problems. You have to take research problem. But here, if you have to write an article in magazine, then that is, hello? 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 So that you have then you have to magazine articles, it means that there would be less analytics, there would be analytics, there would be historic account, and there would be applications, and it would be written for a wider class. So that is magazines. First you read magazines and then go for transactions. So in that case, are that only that you are focusing on transaction papers and cryptic books. So you cannot explain in a better way. So you can give a good talk, great presentations if you read Control Systems magazine. So I recommend you to this. And then there is 23 means volume 20, and you can say issue is means that the 3 means that it goes from year wise and then month wise issue. So in that case, page number this and 2003. This was published in IEEE Control Systems magazine. Originally, there is in control, famous control researchers, they give their talk in Bode lecture. They give in the honor of Bode. They give lectures in CDC. There is one conference that is you can say that the uh, means that the Conference on Decision and Control, that is CDC, and CDC that there is specific lectures are organized every year. Every year CDCs are organized. It is IEEE conference and it is too analytical conference. The standard is very high. And then after that, the one lecture is organized, that is Bode lecture. And first Bode lecture, it was given by Gunter Stein. And Gunter Stein, he is academic and also industry researcher also. He is working with Honeywell. So that 1989, in the month of December, that he gave a talk, means in that conference 1989. This lecture, this lecture, it was widely popularized, and later that the magazine decided to publish this one 2003. So you can see respect the unstable. It means that when you have to basically, just I explain, this is about stability of the system, number one. This is about the sensitivity analysis, and that is about the robustness of system. So if you have to test the robustness of system, robustness, it means that there is a system, simpler language, and its parameters are changing, but controller does not change its parameters. So that the set point means the response achieves the set point without modifications, without changing in the parameters of controller, irrespective of plant parameter variations and effect of input disturbances. So that is the meaning of robustness. So robustness, it is a requirement of control systems. If you write any paper, then people, they talk about its robustness, how you have tested robustness. So many ways people they answer, and many methods are available. If you write any paper, then always you include robustness analysis, and always that you include that the convergence analysis. Otherwise, that paper remains incomplete. So robustness analysis, convergence analysis, computational time, restrictions what you have imposed, all these are important questions that they ask. Stability analysis, sensitivity analysis. So in that case, if you are attempting on such problems, so that Bode's sensitivity integral, respect, in that case, respect the unstable. It means that if you go through the paper, whole paper discusses on two sets of Bode's results, and in that case, that is about system is unstable, there is no NMP0, and system is unstable and there is NMP0. So in that case, he discussed a set of two equations. Equations are very simple. Bode's sensitivity integral, there are two integral equations, and it is a set of two equations. It is very simple, but in that case, if you see its power, then very much it is powerful. There is famous name that the one event in USSR, there is Chernobyl nuclear reactor, and there were several spacecraft which were on test flights. They crashed, and that led to loss of lives. So in that case, their failure, their control system failed. That analysis, it was made using, that can be made using that the sensitivity integrals. So there were two Chernobyl nuclear reactor, and spacecraft, means that aircraft example was there, and it crashed, and that led to means that there was some problem, its control system failed. So because of failure in control system, that may cause loss of life. So how to prevent? So that can be prevented after analyzing how it has happened. So its analysis, in control perspective that you have to go for. Physicists will also analyze, mathematicians will analyze, technologists will also analyze, and control theorists also analyze. So control theorist analysis, it was in terms of sensitivity integral, and they applied Bode's sensitivity integral. And what about the robustness? So whether the system is robust or not. So before putting that any control object into operation, you can test the robustness of the system, and robustness of the system that you can study in the framework of sensitivity integrals. If system is more less sensitive, it means that it is more robust. So that is the point. There is a set of two equations, and using those two equations, you can study sensitivity of those systems. If it is less sensitive, so you can prefer that control system, and then it leads to robustness analysis. So for robustness analysis, you can use Bode's sensitivity integral. For robustness analysis, Bode's sensitivity analysis or Bode's sensitivity integrals, they have proven useful and found applications in famous events where control system failed. And where you can find in this paper, Gunter Stein, Respect the Nestable. And there is another paper, book by Graham C. Goodwin, Control System Design. You can find Bode's sensitivity integrals. So this is very important. Those who teach control theory, those who are control educator, they have to consult this book, and they have to tell their students at least they should read this paper. It is very useful. In France, Germany, I have seen that some of control theorists, they recommend this paper in their class because it is very simple result, but its power was shown to analyze many famous complex events. Any feedback system is there, its control system fails. So for analyzing that the failure of control systems, you can adopt these two results. So I think that this is, I have spoken on this. I recommend strongly to read this paper. There is only two methods, and proof is there. Proof, it is not given in that paper. If you are interested for the proof, then you can find in a book by Gunter Stein, means the Graham C. Goodwin. So that is the concept that you can means that the learn. So it is there, and so that is the concept. So I recommend you read this. It is very less studied, but at least MTech students, they can read this, and you can write paper also. That one paper that I wrote, that reviews in a very simple journal, but I also commented on this Bode integral. So you can see that paper that the one of my PhD students that wrote reviews, and that you can say control and optimization. So there is one journal that you can find, or you can visit Google Scholar with my name. So you can find some comments are there, but I have taken the ideas from these two papers, that Gunter Stein and Graham C. Goodwin. So source is this one I'm sharing with you. You can see this. So recommend this. These are papers which are famous papers. And then further, if you wish to understand history of control, how the subject was evolved, then there were two persons, that Richard Bellman and Robert Calawa. That Bellman, Hamilton-Jacobi-Bellman equation. So in that case, HJB. So that is dynamic programming for control. So control theory. So Bellman also contributed to that. So he has compiled classic papers on control in 1920. And then in that case, he discusses within this compilation, you can find the work of that the whom, you can find the work of that the Maxwell. So they started their paper from Maxwell on the governors. This is the oldest one, but you can find this is the first compilation. Now later that there was another compilation, 25 seminal papers, 1932, means that 50 years, you can say 49 and then 50 years. So in that case, that the 50 years compilation, what work was done. So 25 papers they have selected, 25 papers, 50 years. So it is there. And now I think that the, again that the 2031 or 2030, there will be similar compilation would be there. People, they would be compiling. So what are the best papers in control that you can find in this compilation? 25 seminal papers, 1932, 1981. So first they were published and then it came in books. So it is there. So these are the two recommendations. These are the papers. These are the compilations and books you can find. So that you can see. Now that I will talk more about that what? More about general. I will pose some basic questions in control. These were historic account, philosophical discussions, transfer function and state space technique. Transfer function, that is for LTI system. Any system, if it is LTI, observations are linear, then in that case you can design by a means first you have to find its transfer function. So in that case, transfer function that holds for that the LTI systems and linear observation equation. If system is LTV, means time varying system is there, it means that its parameters are changing with time t, then in that case whether you can find transfer function, number one. And you can say whether that you can say if system is time invariant but it is non-linear, whether you can do achieve its transfer function, whether system is time varying and system is non-linear, whether you can achieve its transfer function. These are the questions. So I will answer directly. So that the state space it is there. So state space it has no limitations. It has universality. And there is another method of design, transfer function based design and state space based design. And then you can say combination of transfer function and state space. So our question was control then and now. So before 1960, it was then, means up to Bode and then his work, it pursued 1960. After Rudy Kalman, that we adopted state space techniques. So state space techniques, most of the control algorithms that were designed, our control systems were designed that exploited state space techniques after 1960. Before that, transfer function technique was there. Nowadays, a combination of transfer function as well as state space both are there. So before 1960, there was transfer function. After 1960, state space became popular, and then after now that the combination of that the transfer function and state space are also being used. So there are many ways people they do. So that is the I wrote control then and now, then transfer function based, and now that the state space based as well as combination of state space and transfer function. Still people they work that only transfer function based. So because that if you see state space setting, so Kalman filtering if you talk about, then in that case it exploits state space model and stochastic evolutions, linear observation equations that he exploited. So in Kalman filtering framework, that is state space setting. Kalman controllability decomposition principle, that is also state space setting. Kalman observability decomposition principle, then again state space setting. So that these are there. So 1960, then and now. Then means that till 1960 or before 1960, transfer function was popular, and 1960 onwards, state space setting became popular because state space setting it has wide implications. So that is the concept, and the point is that the transfer function that holds for time invariant, but state space that it holds for time varying, time invariant, and linear, non-linear. So that the state space setting it has wider framework. So that is before 1960 and after, how people they did control and transfer function, its usefulness and limitations, state space usefulness and its applications. So these are important questions. So what question I have posed, if a nonlinear system is there and you have to control it using means that the transfer function, whether you can do it, then answer is yes. Means transfer function concept generally it is taught for LTI system, linear time invariant system, but transfer function you can achieve for nonlinear systems also. How you can achieve? So in that case, if nonlinear systems are there, if somebody wishes to write, then they can write. If nonlinear systems are there, then achieving its control becomes a complex problem. So there would be certain linearization techniques. And once you introduce certain linearization technique, And once linearization means approximation.
Am I audible? Am I audible? Kindly confirm if I am audible.
Yes, ma'am, you are audible.
Okay, sir. Professor since Sharma sir, you are not audible.
Sir, your voice is not coming, sir. Sharma sir.
कन्वोकेशन का तो कन्वोकेशन का जो है तो हो जाएगा तुम्हारा अभी 20 तारीख को जो है तो डायरेक्टर जो है सीनेट का मिनट्स आया है वो जो सर्टिफिकेट साइन हो जाएगा तुमको मिल जाएगा इश्यू अक्टूबर 20 है ना अक्टूबर 20 इस मींस दैट दी अमित पटेल से मिल लो आई थिंक दैट मेरा जो वर्ड्स है वो जैसे साइन हो जाएगा 25 तारीख के अंदर मिल जाएगा पर वो अमित पटेल से पूछ लो क्या हो गया अब देर से सुनाई दे रहा है आवाज की नहीं दे रहा है
Yes sir, you are audible. You are audible sir.
हाँ ओके कभी कभी दिक्कत हो जाता है और सब ये सब दिक्कत होता है ऑनलाइन में एनीवे दैट इट इज ओके समटाइम्स इट इज ड्रॉप्ड इट इज फाइन सो दैट दी अगेन आई एम बटना है तुम थोड़ा अभी खत्म कहां क्लिक कर दे रहते हो काम दैट इज देयर so it is there so in that case that the if nonlinear system is there then you have to apply certain approximations and once approximations are there then you have to study its convergence and then after you have to study its computational burden also so that the nonlinear problems are there any nonlinear problem if you are attempting then in that case you have to go for certain linearization techniques linearization does not mean that linearization means that this leads to bilinearization multilinearization it offers simplified analysis but that it means that the preserve some of the nonlinearities also so first linearization then convergence analysis then computational part that you have to study so now no nonlinear problem can be brought into the linear form ultimately you have to go for certain linearization technique so how to achieve if nonlinear systems are there I talked about system is nonlinear you have to achieve its control so first part I'm telling you the procedure that the nonlinear system is there then after you introduce linearization technique and after linearization then you will find certain bilinearized or that the alternative means that the description of nonlinear systems that you arrive at bilinear systems and from bilinear systems there is another property that is Volterra systems and from Volterra systems you can recover that the transfer functions so there will be first order transfer function means that the standard transfer function for linear case there is second order Volterra transfer function third order Volterra transfer function you have studied the notation for transfer function HS but here you have to study H2, S1, S2, S3, S1, S2, S3. So in nonlinear problems, terms become unmanageable also. That is the problem of nonlinear systems. What are the curse of nonlinearity? In that case, you have to go for certain approximations, you have to study its convergence, you have to go for understanding its computational burden, and then term also becomes unmanageable. Their realization also becomes difficult, but that they have means that tells more accurately, that accommodate more qualitative characteristics. So that is the reason. So in that case, answer is yes, and certainly that I wrote that what it is means just approximation. Here under the approximation, then utility of approximation, you can say convergence analysis, computational burden, and then after that you have to go for that the what? You have to go for that the bilinear form, and once bilinear form is there, then you go for Volterra form, and from Volterra form you go for that the computation of that the Volterra transfer functions. Transfer function, second order Volterra transfer function, and higher order transfer functions. And once you have transfer function of the plant, then you can design its controller. Then you design the controller. So huge process is there. There are means that some dial, and there is one person dial A or dial what you say. In Automatica wrote one paper long time ago about how to achieve that the control of nonlinear systems using transfer function. So that is the point. Nonlinear system is there, so some approximation, and after approximation or linearization, that you arrive at bilinear form, and bilinear form that you arrive Volterra form, from Volterra form transfer function, and from transfer function use that you design controller, IMC controller, IMC controller for nonlinear systems. So that is the step. So this is there, you can say these are simple questions, and just I post, I think that there was clarity in this. And these are some means that the papers, you can say H quotes Chernobyl accident seminar notes, and this you can say that the Chernobyl accident, any event happens, then what about control perspective analysis? Anything happens, you can analyze that incident using control perspective. So Chernobyl nuclear reactor, its failure, so that the control theorists they also analyzed, and which technique they used, Bode sensitivity integral. So that is the concept. So that this you can say now that the transfer function for nonlinear systems that we have studied, we have discussed. Now there is another part, that is after 1960 onwards, if you say, then in that case that the then and now. Now means that what Rudy Kalman did. So Rudy Kalman in whole control study, control theory, that he used transfer means that state space setting, not transfer functions. Though he worked on linear models, but his models that the transfer function, if it is there, then you can recover that the its state model and state model to transfer function, because since he used in his analysis linear models, because linear filtering, linear approaches, it is there. But for linear transfer function state space both, but he preferred to have state space. So in that case you can find Kalman filtering, and Kalman filtering it becomes famous in Apollo mission in 1971. It was discovered in 1960, but 1971 in Apollo mission, Kalman filtering was used to achieve that estimation of that the trajectory of that the you can say that you can say spacecraft. So that is the point. So Apollo mission, it was used and he became celebrity. So it is there. So I mean to say that Rudy Kalman, what technique that he used is state space setting, and it is under the influence of noise. So that is '60. Hello.
Yes, sir.
So,
Yes, sir. You're audible. Audible, sir.
okay, fine. Just you keep on telling. Sometimes it is dropped.
Sure,
So
sir.
this I
Sure, sir.
wanted to say, that is what is the demarcation line 1960 before and after. What were the technique? Transfer function. Later, that is state space technique and state space as well as you can say transfer function both. So these are from first principle. Now people they are doing machine learning and data driven control. But the point is that they form first principle that cannot be ignored, because first principle, then after data driven control. So that is the point, algorithm part. So from where that algorithm will come? Algorithm, data driven control is there, despite that it uses certain algorithms, and those algorithms that can be generated from the methods based on first principle. So it cannot be denied. Algorithmic existential mathematics, algorithm, and then after library functions, and then after machine learning techniques. So nothing is useless, everything is useful, and world is changing very fast. So you can do data-driven control, but do not think that data-driven control that is isolated from that these control from first principle. There are connections. You have to create connections. So after 1960, as we have discussed, Bode's sensitivity integral, and then after Nyquist plot, and then on the governors, these were famous results. After 1960, what were the famous results? So there is Hamilton-Jacobi-Bellman equation. So there is Hamilton-Jacobi-Bellman equation, Riccati equation, Kalman filtering. All these are means that the famous results. Control now means that you have to study what is Hamilton-Jacobi-Bellman equation, what is Riccati equation, what is Kalman filtering. Because that the Hamilton-Jacobi-Bellman equation, you can say what it is. It comes in dynamic programming from for the control theory. So there is Hamilton-Jacobi-Bellman equation. Later that for stochastic case, HJB was derived. Now Hamilton-Jacobi-Bellman equation, it is not only control theory it comes, it has found its applications in viscosity solutions in mechanical engineering, in viscosity solutions, and then game theory, those who are doing means non-cooperative differential games, and then you can say interactive particle systems in physics. Also Hamilton-Jacobi-Bellman equation, it comes. So it comes in control, it comes in game theory, it comes in physics, it comes in that the you can say that the mechanical engineering. So that is why people they keep on working on Hamilton-Jacobi-Bellman equation. Hamilton first, Hamilton the same person, Hamiltonian, Hamilton, then Jacobi, and then after Bellman brought to control framework, and Kalman also worked on that. So Hamilton-Jacobi-Bellman equation, it comes in dynamic programming for optimal control. It is a first order nonlinear PDE. It is a first order nonlinear partial differential equation, not linear partial differential equation. Somebody says that what is Hamilton-Jacobi-Bellman equation, then you have to tell that it is first order nonlinear partial differential equation. So nonlinear first order nonlinear partial differential equation, it is there. It is very powerful result, do not forget it. Everybody must know what is a JV. So it is first order nonlinear partial differential equation. It comes in that the dynamic programming for control theory. It is famous result. People they are working on a JV and that keep on working. Not only control theory from any area that it comes. It is very powerful result. That is one of the most power. If you select that the powerful results of control, so it would be there. Riccati equation that is for regulator design, LQR. But the Riccati equation, it has the origin Hamilton-Jacobi-Bellman equation, quadratic function, or that the performance measure quadratic function, and system is linear. It may be time invariant, time varying. Then after that, in feedback design, feedback parameters, that is regulator. Regulator means that it is a feedback parameters. Regulator design, it means that it's parameter design. It means that feedback designing that can be made, feedback parameters, they evolve, they satisfy, obey certain rule. So in that case, It is a Riccati equation. Riccati equation that you can prove by adopting Hamilton-Jacobi-Bellman equation for deterministic case, quadratic functions, positive definite symmetric matrices, and then after that you can find that the linear system means that the any system is linear is there, time varying or time invariant, you have to go for its control and you have to control it optimally. Then after that you have to use Riccati equation. Riccati equation, it is a regulator design problem and that gives about the parameters of the feedback parameter evolutions that it tells. So Riccati equation, it is a consequence of Hamilton-Jacobi-Bellman equation. Got the point? But Riccati equation has that much power that it does not come only. It has not only relations with Hamilton-Jacobi-Bellman equation. It comes in various ways in control literature. It comes in Kalman filtering also. From Hamilton-Jacobi-Bellman equation, you can prove Riccati equation, and then from Kalman filtering, automatically you arrive at Riccati equation. Kalman filtering is a set of two equations, and there is variance propagation of linear stochastic differential system in combination with linear observation equation that is governed by that you can say a Riccati equation. So in that case, variance evolutions of linear stochastic differential system in combination with linear observation equation, it obeys Riccati equation. So Riccati equation, it comes in Kalman filtering. If system is linear with delay element, then after you have to achieve its stability analysis. So stability is governed by Riccati equation. So same structure comes for different perspective. It comes in filtering problem, it comes in control problem. Control means that you can say stability viewpoint, it comes, and it comes in optimal control sense. Structure will remain same, but notations, interpretations, that would be different. So you can say Hamilton-Jacobi-Bellman equation, it is one of the most powerful results of control. And then after Riccati equation, it is also most powerful results in control for linear control theorists. Kalman filtering, you know, it is celebrated results in control. 1971, this was used in Apollo mission. But as far as research is there, Hamilton-Jacobi-Bellman equation, still it has too much potential to work. Riccati equation, it has too much power to work. Kalman filtering, it has also too much applications. Now people, they have gone beyond, but these are the things you must learn. So these are the top results of control and then and now in two parts that we have bifurcated. If you are interested for the Riccati, yes, Hamilton-Jacobi-Bellman equation, it is a nonlinear partial differential equation, PDE, like mechanical engineering Navier-Stokes equation, that is also a PDE, that is second order nonlinear PDE. And here Riccati equation, that you can say this Hamilton-Jacobi-Bellman equation, it is also a PDE, but its order is 1 and it is nonlinear. It is not linear PDE. Got the point? And then after Riccati equation comes in the optimal control of linear time varying system, and its origin is, it begins from Hamilton-Jacobi-Bellman equation. So Hamilton-Jacobi-Bellman equation is nonlinear PDE. Listen carefully. And the system is linear time invariant. And Riccati equation is again a nonlinear ordinary differential equations. So differential equations are many versions: partial differential equation, stochastic differential equation, or nonlinear ordinary differential equations. So ordinary differential equations, partial differential equations, or stochastic differential equation, it comes. So system is linear time invariant or linear time varying. Riccati equation is nonlinear ordinary differential equation, and HJB is first order nonlinear partial differential equation. So differential equations has different versions. So you can see that the Riccati equation, and for linear case, this is the structure, nonlinear ordinary differential equation, but it comes from where? What kind of system? It comes for linear systems. For nonlinear systems, that you have to design generalized Riccati equation. Here nonlinear word is there, then you cannot say that it is useful for linear systems. It would be coming up for nonlinear systems. It means that here nonlinear word is there, nonlinear ordinary differential equation. You do not say that it is a control scheme or feedback design system, method or equation that is for linear nonlinear systems. It is totally for linear systems, but it comes mathematically somewhere. So for linear systems, linear time varying and time invariant, this nonlinear partial differential equation comes. But you can ask for nonlinear systems how to design, then in that case not Riccati equation, that is generalized Riccati equation comes. So here it is there, and these are the famous name, this S. Bitani, is a Lau and Gen C. Willems. So Riccati equation, it is not merely equation. You can find greater detail in this book. Donald E. Kirk, that is in final year people they teach, it is famous book. You can understand from here. I have learned that the Hamilton-Jacobi-Bellman equation from Donald E. Kirk. Got the point? So it is a famous book and well written book. So you can find this one, and then you can see that the ignoring stochasticity. Now that there is another topic that I have taken, that is stochasticity part, that the control then and now. Then it means what? Then it means that previously, before 1960, now after 1960, and the famous results famous work we have seen in terms of that the body, and famous results after 1960, and these Hamilton-Jacobi-Bellman equation, and you can say Kalman filtering, Riccati equation, all these were based on controls that was discussed in 1960 later. And then after Bode sensitivity integrals, Bode's ideal transfer function, Bode plot before 1960. So these are the things. There is another class that is stochasticity, turbulence, that it comes. So how to handle all these control what we have discussed, they do not talk about that the handling turbulence in control problems. So that can be handled. It can be means that you can say certain formulations are required, different mathematics is used. So that is Brownian motion. What is Brownian motion? You have studied that the Brownian motion, that is for that the pollen particle in physics. But now Brownian motion process, it has found its applications to model noise or random perturbations, helicopter rotor dynamics. Its turbulence should be there. So turbulence that can be modeled using Brownian motion process. Turbulence is a random process. Brownian motion process, that is also a random process. So I will not discuss much more, but if you are interested, then Brownian motion process, if it is there, you can understand Brownian motion process that has proven useful to model effect of noise and dynamics of the system. So it would be there. This is also known as that the means stochastic control part. Stochastic control part that also started its research 1960. So these are the properties of Brownian motion process. It needs a different class and lecture, so that you can say these are the mathematics behind. I will not discuss much more, but there are certain calculations, moments you can say. So if some other talk is there, so we can discuss later part if some other talk is there. And here I wish to close my talk, and this is, if you are interested on filtering and all, so I have shared this. Jazvinsky book is there, and future directions then and now, what would be later. So you can find stock prices, stock, those who are interested, share prices. There is algorithms they are using, and they are using algorithms for what? Stock trading is there, some computer program would be there, and program basically its origin is that algorithms are there, and those algorithms means that you can say means that from algorithms then it has to be programmed on the chip, and then after library function. So those programs that they use, they borrow the idea from control. So what we are doing, it has tremendous power and huge potential. So you can think of control algorithms, they are useful in stock trading research also, as stock trading also. Biological systems, you have to go far. It means that biological systems are there, how they communicate, how they react, how they observe and how they live for their survival, so that it can be control theories there also. So control theory you can apply. Got the point? You can understand that the control in biological systems, machine learning methods, quantum control, whether quantum computers are possible. So that is the question, and people, they are working on that. So these are the later parts, and perhaps that the 20 years, 30 years, most of the people, they would be working on quantum control, and machine learning, it has become popular. The data driven control, because data driven control, machine learning, that is that the linked control in biological systems. Control in biological systems, you can say biological systems are there, so how to apply feedback system to achieve the performance. So that is there. So biological systems you can understand, and then if you have to control, then you have to apply the systems and control method. Biological system is there, that is uncontrolled system, but you have to control it, then you have to apply the means systems and control techniques. So these are the methods that you can see, and this list is not control, means that complete, and you can see this control then and now and later. So if you have any question, then you please ask. Okay.
Thank you very much, sir. It was such a nice lecture.
So that the time was short, otherwise I could have spoken more, some analytics and all, that the how to calculate expectations, and then a stochastic process, and then moments, and then what is the differential equation in case of stochasticity rather than deterministicity. So that some unusual results which are not found in the books, we have to discuss. If there is a time, then we can talk later also in this lecture series or some future. So it is there.
Sure, sir. Sure. So, dear participants, if there is anything, any question or any
question is there, then you please ask.
Yes.
Yes, questions, please.
You can unmute yourself.
You ask. There are many questions in the mind that it comes. So you can ask. The questions are always correct. Hello. Yes, please. So no questions are there. So these are the things that you can ask, and we will meet later. And thank you, participants, and thank you, organizers. Professor Sekhar, Professor Abdesh, they are our close friends. So they invited me, and on this slide I have spoken many times, because these are the crux. And again, that we can bring certain things, because in control, that the too much analytics is there, applications are. But one thing I want to say, that the think from control viewpoint. If anything happens, any event happens, then you think what is how means that the control techniques that would be useful to solve, to address this problem beyond the classroom, beyond the society, solving societal problems by using the methods and techniques of control for humanity, control for society. So we can prove our usefulness. Otherwise, people, they say it is merely equations. So control for humanity, control for the society. So how that any problem is there, so you think from control perspective. Then what ideas you have, you can think of, and based on those ideas, you can give solutions to them. So then in that case, control will prove for the society. You can try. Sometimes you may, sometimes you not. So if any event is there in the society, so find out its solution using the methods and techniques of control. That is the message. Okay?
Yes, sir, sure. In fact, that is the ultimate objective of control.
Yes. So I'm leaving. Thank you. And if somebody has, then they can write this email. Okay?
Yes, sir.
So we will talk in the evening, organizers and participants. Thank you.